We found that by taking a p-type material and an n-type semiconductor material and bringing them in close proximity to each other, we form the basis of a diode. And inside of the diode, because of the different charges that are available to move throughout the material, we establish a built-in electric field or built-in potential at the junction between the p-type and the n-type material. We also said that we could represent this from a band energy perspective with the bottom chart right here, wherein the electrons that are free in the n-type material to move throughout the crystal do not have sufficient energy to overcome this built-in potential, because the electric field is going to be in this direction. They don't have enough energy to overcome this potential barrier, and therefore they're going to remain on the n-type side of the material. And the holes are going to experience the same type of thing. They're not going to have sufficient energy to get under this potential barrier, and therefore they're not going to it's not going to result in a net current flow, because we have no motion of charges once this internal potential is set up inside the semiconductor at the junction. The other thing that we pointed out was that to form these band energy diagrams, we assumed that this junction of the p-type and n-type material was at what we call thermodynamic equilibrium, meaning that there's no temperature gradients and we have no applied voltage across either side, either the anode or the cathode of our diode. Now, what happens, why the Fermi energy level is so important, is that the Fermi energy level is a property of semiconductor materials, or actually any materials, that we can measure directly. The Fermi energy level, or rather the difference in the Fermi energy level from either side, tells us, is measured by the voltage. So we can take a voltmeter directly and measure the potential across the anode and cathode. And if it's at thermodynamic equilibrium, we're going to have no potential difference. Even though there's this built-in potential right here, it's only in this junction region. It doesn't exist further out at the anode or cathode of the material of the diode. So when it's in equilibrium, we have no potential across this diode. Now what we're going to do is we're going to look at what happens in the forward bias and reverse bias conditions. So we've taken a look at these. You've seen some of these in our lab exercises, and we've talked about how they behave a bit. Now we're going to see it from the materials perspective, and hopefully gain a little bit more insight from our studies of looking at how semiconductor materials behave. Okay, so we've taken this p-type and this n-type side, and what we're doing here is we're going to forward bias this diode. Okay, and we're going to apply a greater potential across the anode relative to the cathode. Now, again, in our intrinsic material, or excuse me, in our unbiased material, where we are not applying any potential across the anode and the cathode, the Fermi energy level remains constant. Now, what's going to happen when we apply a forward bias, what we're going to do is we're actually going to start moving the Fermi energy level of the p-type relative to the n-type. And in this case, what's going to happen is that we're going to shift the Fermi energy level down on the p-type side, because we're applying a positive potential relative to the n-type side. So the n-type side, since it's more negative, it's going to, well, we could say it remains the same, or it's going to shift closer. It's going to shift upwards relative to the p-type side. Okay, so what we've done here is I'm going to take the Fermi energy level for the p-type, I'm going to shift it down a little bit relative to the Fermi energy level for the n-type side. So that's going to go this direction. It's opposite of what we think. It's opposite of what our conventional current direction is, and that's because this graph is showing us electron energy. All right, and if we apply a more positive potential over here relative on the anode side relative to the cathode side, what we're really doing is we're increasing the energy of the electrons on the cathode side and decreasing the energy on on the anode side. So that's what happens there. So I've taken them and I've shifted them a little bit relative to each other. All right, and then what I'm going to do is I'm going to draw redraw my band energy diagram. And what I'll find is that there's less of an energy barrier now. All right, so before we shifted these Fermi energy levels up, there was this there was this significant energy that the electrons would have to overcome to move through the electric field, and the same thing with the positive holes over here. But now we've decreased, by applying this potential, we've decreased the height of this energy barrier. So now, since we have electrons populating this conduction band, because we've lowered the energy barrier, a greater proportion of those electrons can actually make it across the electric field, or across the built-in potential, and a greater number of holes will have sufficient energy to make it to the other side of that built-in potential. Well, since we have holes moving in this direction and we have electrons that can move in this direction, we get a net current through the through the diode when it is under the forward bias condition. And the number of electrons and the number of holes that can move across that built-in potential field is going to increase drastically as we increase the bias, as we bring the Fermi energy levels further apart, and we flatten out the conduction band and the valence bands more. We've seen this behavior before in the forward bias condition. As we increase the voltage, the current that passes through the diode increased exponentially. And that's what we see. It can be described using this band energy diagrams that we see right here. The other thing that we can think about that's happening here is that if we look back in our material, what we're doing is we're actually decreasing the width and the strength of this electric field region right here. So the number of charges that have accumulated in the area around the junction is actually going to decrease because we're injecting more positive charges onto this side. So we're going to decrease the net negative charge on this side, and we're going to decrease the net positive charge on this side. So overall, we're decreasing the strength of the electric field so that more electrons and more positive charge carriers can pass through that barrier. Now, what happens on the other side when we do the reverse bias condition? Well, the reverse bias condition, instead of separating the Fermi energy levels like this, since we are applying a negative potential relative on the anode side relative to the cathode side, what we're going to do is end up swinging the Fermi energy levels apart the other direction. So here, the p-type material Fermi energy went down a bit relative to the Fermi energy level for the n-type side. Here, the opposite's going to happen. So we're going to draw the Fermi energy levels for the p-type and the n-type side. Okay, and the p-type side, what we're going to do is draw the valence and conduction bands. So the valence band there, and here's the valence and conduction band for the n-type material, and then connect those two. And you see what happens is that when we apply a greater and greater reverse bias, what we do is we increase this energy barrier. So now these electrons that are populating the conduction band are certain to have no energy, or insufficient energy to surmount this energy barrier here, and the same thing with our holes that are populating the valence band. So there's no way for these charge carriers to move across that energy gap, or excuse me, across that, not across the energy gap, across the electric field here. And we've seen this before when we've looked at our lab in the reverse bias condition, where there was essentially no net current flow through our diode when we reverse biased it. All right? And the reason is because of this energy barrier. In the physical sense, what we can think about going on here, because we are adding more negative charges to the p-type side and more positive charges to the n-type side, this is causing a widening of this area where we have the electric field, and a strengthening of the electric field because we're increasing on the N-type side, we're increasing the number of total positive charges that are accumulated near the junction, and we're increasing the total number of negative charges that are accumulating near this junction. So we're widening we're making that area larger, so it's a further distance for the positive and negative charges to travel through, as well as strengthening the total electric field. So that's the basics behind what happens when we take a p-type material and an n-type material and bring them together to form a diode. And the discussions of energy levels and how the charges form in this built-in potential region is important to understanding the physics behind how things like diodes operate. The next semiconductor device that we're going to look at will be a combination of diodes.